Anyway, so our one sample t-test. Let's kind of go through a hypothetical example. So I'm interested in if the mean SAT score for high school seniors in Maine is above average, above the national average. I know that the mean for all seniors everywhere in the world is 1,000. Don't ask how I know that. I'm Ted Coladarchi. You work for Ted, right? There you go. At least for the next few months. Institutional
retiring.
research.
I'm not getting fired. Just to clarify.
I said that bad. That sounds bad. Ted's retiring. He's institutional research. So like he knows the SAT scores for all the students at UMaine. But let's say we don't have that. But anyway, so I know the average for everyone is 1,000. I sample 144 seniors in Maine and find that their average is 1,050. Kind of sound familiar, right? This is kind of continuing with some illustrations from last week, but we're going to take it a step further now. How large, and I need to ask myself, is that big enough? Maine kids scored 50 higher. Is that big enough? Or is this just kind of what I would expect to see? So let's go. We kind of talked a lot about this. How big of a difference did I see? X bar minus mu is just 1050 minus the 1,000, gives me a 50. That's how big I saw. How big of a difference did I expect? So now we're back to the standard error of the mean. Kind of what's the standard deviation of those means? So I need to look at the standard deviation for my sample. Let's say the standard deviation for my sample was 200. Right, that's the scores I've observed. My sample size is 144. So I take 200 divided by the square root of 144 divided by 12. And that gives me a standard error of 16.667. So, kind of to do the t-score, I write it out. T with n minus 1 degrees of freedom, so I had 144. So t with 143 degrees of freedom is 1050 minus 1,000 divided by the standard error of the mean. Works out to be exactly 3. That's because I made up the numbers to do that, keep the math simple. So the results, t with 143 degrees of freedom equals 3.0. This is exactly kind of how you write it up for your paper. Is that big or small? Kind of what does it indicate? Now again, remember, that t-score just tells us it's some very abstract number that is just telling us how likely is it we would have got an average of 1,050 if the real average was only 1,000. So, well, we can do it with the p-value. What's our p-value? So again, the probability, the p-value is that probability of getting a test statistic this extreme or more extreme than what we obtained. So here's my test statistic, that extreme or more extreme if the null is true. And those are kind of two important points, so I even wrote them in different colors to kind of make that kind of clear. So that's kind of conceptually. In practical terms, for our question, it's the probability of obtaining a t with 143 degrees of freedom, a t-score of 3.00 or more, positive or negative, more than 3 or smaller than negative 3. If the mean for Maine seniors really is only 1,000, right? So if the null is true, that's if the null is true. So there's my test statistic. Here is if the null is true. So my Excel code for the p-value, which we talked about a minute ago, I just open up Excel, I type in equals t dot this dot 2t parenthesis 3 comma 143. You don't have to put the periods. I just did that just to make it clear. Kind of points you back to where it came from. And it pops back and tells me p equals 0.003. That's my p-value. A lot easier than fumbling with some books. What that P of 0.003 means is that I'd only get a result this extreme or more extreme 3 out of 1,000 times, or 0.3% of the time, if the null hypothesis is true. So assuming my alpha is 0.05 and I'm comfortable rejecting the null when it's true 5% of the time, where my probability has to be less than 5% for me to reject the null. Well, this is way less than 5%. So I'm rejecting the null. You can kind of visually see it. Well, another way we can do this is with the critical t-scores, just like before. And again, you might see, well, we just answered it. Why are you having more? But again, I want you to get comfortable with the notions of critical t's and kind of how we can use them. So I said, okay, well, I asked Excel, my degrees of freedom is 143. My alpha level is 0.05. Tell me what the critical t-score is. How big does my t need to be to reject the null? So I asked that of the Microsoft wizards, and here's the code again. You type in the 0.05. That's my alpha level, and it'll say like probability if you look at the little pop-up stuff with Excel when you're doing it. But remember, alpha is our probability. It's the probability that we need to reject the null. That's why it's 0.05. So we say my alpha is 0.05, my degrees of freedom is 143. It pops back and says 0.1. It says 1.977. It doesn't actually. It's not smart enough to give you the plus or minus sign, but you just have to remember it's positive or negative 1.977. So there's those critical t's. Anywhere in between is just too common. Way too much possibility of it happening somewhere in here. But RT was 3.0. It's way out here in our reject region. We reject the null. So again, kind of it all ties together. Questions? That's the one sample t-test. You may ask yourself, again, we're going to see this a lot. Well, actually, it'll be interesting when you first see it. Well, now you kind of click, that's a one sample t-test, even though it doesn't tell you it's a one sample t-test. There's also two sample t-tests. Two sample t-test, as you can gather, rather than compare one average to a population average or one average to some other value, right? It doesn't have to be mu, as we were saying. It could be something else like 0. The two sample t-test says, well, I want to compare one average from one sample for one population to an average for another sample that reflects some different population. And again, we want to kind of remember when we're taking these samples, our kind of underlying assumption is that they're reflecting different populations. That one sample might be the population of theoretical kids if they got my math intervention program, and the other sample is the population of theoretical kids that don't get my math intervention. Or it could be the population of boys and the population of girls in elementary school. It could be students from Maine, the population of all of them, and students from Wisconsin. But we're comparing, we have two samples that are in some way different. And they reflect two different populations, and we want to compare. We're using those samples to infer back, are those populations different? Sometimes, again, it might be a real population like kids in Wisconsin. Sometimes it may be a theoretical population like kids who might get my intervention. But that's kind of how it's a little cumbersome, but it helps you to kind of understand how it all comes together. There's two types of two sample t-tests. You can see in one case, they're what we call as dependent samples. You might see it called dependent, you might see it called matched, you might see it called repeated. So don't get hung up on the language, on the jargon, because God forbid we all decide on one label for anything and stick with it. But conceptually, what's important is with the dependent sample, there's in some way repeated measures or some way paired measures. It might literally be, often where we'll see it is a repeated measure. It's a pre-test and a post-test. And so you can see kind of like if I've got 30 kids and I'm doing pre-test and post-test, they do a pre-test before they took my intervention, then they do a post-test after the intervention, and I want to see did their interest in STEM education increase. Right? So I want to see, is there a difference between the two pre-tests and post-tests, between the pre-test and post-test? You can see it's kind of with the dependent test, the dependent t-test, each kid is matched up with each kid. There's your pre-test and post-test, and then you've got a pre-test, and you've got a post-test, and I got a pre-test, and I got a post-test. So each test is in some way, each measure of the post-test is matched to one specific measure on the pre-test. That is actually an incredibly powerful design to do matching. Matching is an awesome thing that it drastically increases your ability to detect effects when you can do that matching. Because instead of just comparing me to my post-test to the average over here, I'm able to compare my post-test to my pre-test. So if I'm a kid who had absolutely no interest in STEM, and at the post-test, I'm a little interested in STEM, but below average, it still shows, oh look, my score went up. Instead of, oh look, this kid's still below average. Oh, nothing worked, nothing happened. Now it's like, wow, his score went up, instead of just comparing me to the average. When you do that enough times, you're able to detect very subtle differences. I think I might have mentioned last week, one big intervention we did, that you look at it, if we ignored the pairing, there was nothing there. But once you threw in and looked at the data paired up, the effect was huge. So it's great designs when you can do a dependent, repeated, whatever you call it, t-test.
When you do like after the fact, like not so great? Or?
The matching should be done prior to random assignment or prior to an intervention, kind of, yes. It's not as good to try to match. So
is it still somewhat good? Or?
It depends. It depends. There is how it's, so one thing that you'll often see, let's say I'm doing an intervention out in some schools, and I don't have the ability to, in our intervention, what we did for particularly the new people, we had 43 schools, and we matched the schools based on all sorts of demographic characteristics, all sorts of prior testing, and we flipped a coin. Your school gets this intervention, you have to wait 2 years. You get the intervention, you have to wait 2. So we've matched up each school so that they're two very similar schools. You guys are two awesome, high achieving. Your kids all go to Ivy League schools. No one ever skips class. Your teachers love their jobs. And then you guys hate your, So where you kind of see the comparison. And so we found, that was before, and then we randomized. So another thing that often happens is I just do my intervention with these schools, and then afterwards it's like, okay, now I got to find some comparison because, yeah, your kids' math scores went up, but did they go up enough? So I got to find some schools that are kind of just like your schools, and I go through and I try to match them up and say, okay, this looks like your school did, so you try to pair them. That's post hoc matching. People do it a lot. And it's getting more, well, the downside. One of the, it can completely blow up in your face because there's all sorts of reasons why schools may look similar, but they're really not. So trying to pretend that you'd matched and randomized when you didn't. Case in point, Head Start. Back in the 60s, there were some studies looking at the effect of Head Start where they did post hoc matching. And the people that did the studies were pointing to, oh, look, it's having this wonderful effect, which got a lot of attention, a lot of support. Head Start's doing wonderful. This is great. Other people then came back in and looked at the data and said, well, wait a second, that wasn't these weren't really you're pretending that you ran them, you matched a priori and then flipped a coin, and let's kind of ignore that.
It's not really random.
No, let's actually look at the data without that, and the effects completely disappeared. And the problem was that then, from a practical standpoint, anytime someone came for decades afterwards, when people came out and said, look, Head Start helps kids, here's some studies showing Head Start helps kids, the critics of Head Start quickly pointed to, yes, but I remember in 1969 when X, Y, and Z did their study and it was complete crap. So I don't trust your numbers. You kind of, we meaning academics and in that case social liberals that I like Head Start, shot themselves in their foot by doing bad research. You think you do bad studies, you do bad stats, there's someone out there who's going to notice, and they will use it as a stick against your cause for their cause. It's anyway. So there are problems doing post hoc matching. Sometimes it can work, but you don't know, was this a good time or was this a bad time? Now there's more advanced strategies that have been coming up. We won't get to them in this class, but kind of while we're on the topic. There's approaches that have been gaining favor the last few years that involve, instead of just eyeballing how similar the schools are and saying, yeah, you guys look similar, you can go in statistically and figure out, well, let's see kind of how, in a more statistical sense, how similar are the two schools? Or if it's like kids, how likely is it that this kid would have done the intervention if I flipped the coin? And you can find, and instead of now just saying you're an exact match, you're able to statistically come in and say, well, it's a kind of match, instead of kind of equal weighting. It's complicated. It's been incredibly popular. Well, it's been widely popular, I should say. And there's a variety of ways you can do that sort of approach. There's some, I think, we'll see kind of the staying power it has. I think there's some now that are starting to voice the exact same concerns. That it still doesn't quite, nothing beats the randomized, nothing beats flipping the coin. But that's better than just eyeballing and saying, oh, yeah, you guys look similar. I'll treat you the same. Digression. So post hoc matching has a lot of problems, but people do it anyway. But there's good ways and bad ways. Propensity, what I was just talking about, I guess, so that you kind of, if you're reading something, propensity score matching is one of these stronger tools that people will use for doing. That's one label that it's called, is propensity score matching. There's another strategy called principal stratification that kind of gets at a related sort of issue. That kind of the same thing of trying to find some very similar group. But we digress. That is not part of this class. Then you have, so that's a dependent, then you have independent t-tests, and that's probably most of what we do. That now it's just like, okay, I've got a sample over here, I got a sample over here. They're not some way matched up. There's not something that connects this kid with that kid and that kid with that kid. But it's just two different groups, and I'm looking at I'm plugging them into a t-test. They're unrelated. Individuals in this group are unrelated to individuals in that group. Now, for independent t-tests, because they're not matched one-to-one, you might have 30 kids in this group and 45 kids in that group because you don't have to worry about it. For the repeated measure, it'll be exactly the same number of pre-test, post-test because it's the same person 2 times. They're always exactly the same. One other thing, when you think of the repeated, it doesn't have to actually be the same person repeated. It might be, I'm looking at mother-daughters or husbands and wives and asking them how they think about something. And so it's the husband and the wife and the husband and, that you've got some But the key is there's something that connects one person here with one person there.
Does the number of people taking the test have to be the same pre and post in order for it to qualify as repeated?
Well, yeah, because if they've only got the post, then you can't look at their individual change, their difference between. This really comes down to, you end up doing a one sample t-test based on the difference between the pre and post test. So if you're missing a pre-test, there's nothing to see kind of how much did you go up. If you're missing the post-test, I don't know what happened to your score in the end. So for the t-test, yeah, you need the 2. Okay? We're not going to get into the nitty-gritty of the t-tests. Otherwise, they operate exactly the same way. How big of a difference did I see? One average minus the other average, divided by how big of a difference did I expect to see, the standard error. In this case, it's the standard error of the difference between 2 means instead of the standard error of a mean. Because, right, you got 2, it's kind of how much, if I had an infinite number of samples and calculated the differences between the means across all those samples, what would that standard deviation be? But otherwise, it's exactly the same, exactly conceptually the same thing. I saw this big of a difference between kids in Wisconsin and kids in Maine, and my standard error says I should have only seen the difference this big. Something's going on. Okay? ANOVA.